primary valency is ionizable and it is satisfied by negative ions. How to write the secondary valency? We know that secondary valency are nothing but a number of ligating ligands which forms a coordination bond with the central metal atom. So in that, all the central metal atom which get overlap with the ligating orbitals of the ligands and give rise to the hybrid orbital. And from the oxidation number calculation, we have understood that it will loses how many electrons? Only 2 electrons. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with a unit called coordination compound. Under that, we have discussed about the isomers in the coordination compound. In that, we have understood that what are isomers and we have learnt about classifications of the isomers. In that, we have deeply studied with the stereomeric isomers and structural isomers. Is it right? Yes. Again, in the stereoisomerism as well as in the structural isomerism, we have studied their types. Today, let us move on to the next topic of this unit by understanding the Werner theory of coordination compounds, and lastly we are going to discuss about the limitations of Werner's theory, and we are going to understand more about valence bond. We are going to understand more about what? Valence bond, and also we are going to discuss with the applications of valence bond. Okay. Now let us see what is a Werner theory. So in the year 1898, Alfred Werner was a scientist. He prepared a large number of coordination compounds and he studied their physical, chemical as well as their isomeric behavior of that organic compounds, okay, of that coordination compounds. And he finally come to the conclusion that, and he put the postulate to explain their behavior. So the first postulate says that the central metal atom that shows the 2 types of valencies. So always the central metal atom in the coordination compound that shows what? 2 types of valency. That is known as primary valency and secondary valency. So this is known as primary and secondary valency. To explain what is primary valency and secondary valency, I'll write one example. Okay. So I'll take copper NH3 4 times with Cl2. Okay. This is my complex. In this compound, you can clearly understand that, okay, the central metal atom is a copper, okay. So in this example, you can clearly know that copper is a central metal atom and which has been coordinated by 4 different NH3 ligand, and we know that Cl2 is my counter ion. Is it right? Yes. So now the first step is we need to calculate what? Oxidation number. So how to calculate the oxidation number? We know that for the copper I'll take X plus, so 4 into the oxidation state of the ammonia is 0 is plus 2 into for the chlorine it is minus 1 is equal to 0, and X minus 2 which is equal to 0, and we know that X is equal to plus 2. So oxidation state of the copper is what? Plus 2, and this is known as primary valency. What is known as primary valency? The oxidation number of the central metal atom, which is known as what? primary valency. So I'll write oxidation number of what? Central atom is known as what? Primary valency. So what does the first postulate says? The first postulate says that the central metal atom has two types of valency. One is primary valency and secondary valency. What is the primary valency? We know that primary valency, which is nothing but a oxidation number of the central metal atom. Then what is the secondary valency? Secondary valency in the sense, you know that from this example, the copper is a central metal atom which is ligated by 4 different ammonia ligands. Is it right? So it has been ligated by 4 ammonia ligand and it forms what? It forms a 4 coordination bond with the central metal atom. So I can say that secondary valency, which is nothing but a coordination number, which is nothing but what? Coordination number which are exhibited by the ligand towards what? Central metal atom. So towards the central metal atom, how many ligands are there and how much the coordination bonds are formed, that is said to be secondary valency. So this idea was given by whom? Alfred Werner, and hence this theory which is named as Werner theory of coordination compound. So what does he says? He says that all central metal atom in the coordination compound that consists of 2 valency. One is primary valency and the one is secondary valency. And we come to know that primary valency, which is nothing but a oxidation number of the central metal atom. And we have learned that how to calculate the oxidation number also. Is it right? Yes. And we have also understood that secondary valency, which is nothing but a number of ligands which is get ligated or which forms a coordination bond with the central metal atom, that is said to be secondary valency. So in this example, you can clearly understand that there are 4 ligands will be there that forms a 4 coordination bonds with the central metal atom, and it is nothing but a secondary valency. So we'll understand further now. So primary valency is ionizable and it is satisfied by negative ions. Which means what? We know that this primary valency, which is nothing but a oxidation number of the central metal atom. We know that it is always satisfied what? Negative ions, which are nothing but what? Counter ion. We know that copper will be exhibits in the +2 oxidation state, and if it is loses 2 electron and it is balanced by what? Negative ions, which are nothing but what? Counter ions. So this was a second idea and it is given by whom? Alfred Werner. So what is the primary valency? Remember, always primary valency is nothing but an oxidation number. And we know that oxidation numbers are always ionizable, which means what? When it is loses electron, you know, it can easily get satisfied by negatively charged ions. They are nothing but a counter ion. And remember, you know, when we dissolve this compound, you know, what will happen? The copper will lose 2 electrons and that 2 electrons will be satisfied by whom? Counter ion, which is nothing but a 2-chloride ion. That is why I have written copper, it is exhibiting a +2 oxidation state and it is balanced by 2 chlorine atom. Hence, we can say that primary valency are ionizable and their valency is satisfied by negative ions. Okay. Now, when it comes to the secondary valency, it is known as non-ionizable and it is equal to the coordination number of the central metal ion or the atom, and it is fixed for a metal, and always secondary valency are satisfied by negative ion as well as by neutral ligands or the neutral molecule. So what does the secondary valency tell us now? So from that primary valency, we have understood that when we dissolve such compounds, primary valency can easily get ionizable, which can lose its electron and it is balanced by negatively charged ion. Whereas secondary valency, what is secondary valency? Secondary valency is nothing but what? Coordination number, which has been formed by ligands towards a central metal atom. Is it right? Yes. And it is always fixed. Okay? It is always fixed and it does not easily undergo ionization to produce any ion. But sometimes, the secondary valency also, which is balanced by both this counter ion as well as by the ligands. This is how, we can easily understand the idea about the primary and secondary valency was given by the great scientist known as Alfred Werner. So then he says that primary valency is non-directional, whereas secondary valency is directional. So what does it mean? We know that by using this secondary valency only, we are predicting the geometry of the molecule. Is it right? Yes. That is why we say that this is tetrahedral in geometry. How do you say it is tetrahedral? Because the 4 ligands which forms a 4 coordination bond with the central metal atom, hence the geometry will be tetrahedral. Hence we can say that by using that secondary valency, we can decide the geometry of that complex. But by using primary valency, we cannot decide the geometry. It is help us to know that how to calculate the oxidation number and how does that oxidation number, which is also balanced by negatively charged ions. Okay. Next, the molecules are attached to satisfy the secondary valency have give the characteristic spatial arrangement. Hence, secondary valency which decides the geometry of complex compound. So, what does that indicate? The secondary valency means what? Number of coordination bonds are formed by ligands towards the central metal atom. We know that these ligands are arranged in their own way. Is it right? They are arranged in spatial arrangement. So when they are arranged in their own structure, it will decide its bond towards the central metal atom. Hence we can, by understanding the secondary valency, we can say that what is the geometry of that given complexes. So this was a new idea to predict the structure of the coordination compound, as well as by predicting the primary valency, we can explain about the coordination compound, and it was an idea was given by Alfred Werner in the year 1898. So, hope you all understood with this topic. So, we'll recall this topic by understanding one more example. So, here I have an example of CONH3 6 times Cl3. How do you name it? So, it is hexaamino cobaltate 3 chloride. Is it right? It is hexaamino cobalt 3 chloride. Is it right? Yes. So, from this, first of all, we need to calculate the oxidation number. We all know that we need to calculate the oxidation number of the central metal atom, which is obtained by x plus 6 into 0 plus 3 into minus 1, which is equal to 0. So, x minus 3, which is equal to 0, and x is equal to plus 3, which is the oxidation state of the cobalt here. Okay. So, in this complex, you can see that the primary valency, which is nothing but a plus 3, which is nothing but the oxidation number of the central metal atom. Then, how to write the secondary valency? We know that secondary valency are nothing but a number of ligating ligands which forms a coordination bond with the central metal atom. So, how many ligands are there? There are 6 ligands are there, and all 6 ligands, they are monovalent, which loses one electron towards the central metal atom and forms a 6 coordination bond, which is nothing but a secondary valency. Then, we know that primary valency, which is exhibited by 6NH3 bond, and remember, we know that primary valency is nothing but oxidation number, which is balanced by whom? Which is balanced by what? Counter ion. Hence, I have written Cl3. Okay. Next, and also we have understood that secondary valency, which is satisfied by both ligand as well as with negative ions. So this idea was given by whom? Werner. Okay, and from this entire description we can say that it will be exhibit in octahedral geometry. How do you say it is octahedral? Because there is a one central metal atom and which is get coordinated by 6 ligating ligands and forms a octahedral geometry. This is how for the given compound we can easily explain the geometry based upon the primary and secondary valency. So hope you all understood with the Werner theory. Next, we'll see the limitations of Werner theory. So the first limitation says that a few elements have the property to form a coordination compound. So only in a few coordination compounds, that exhibits their property which shows their geometry. Okay, only in few compounds he has observed this primary and secondary valency, not in all the compound. That was a first drawbacks to the coordination compounds which has been explained by Werner. And he says that the bonds in the coordination compounds have directional property. So what does it mean? We have understood that in the secondary valency which decides what geometry of the complexes. Is it right? Yes. So the bonds in the coordination compounds have a directional property. He does not explain why the primary valence is not help us to predict the structure of the given compound. Next, the coordination compound have a characteristics magnetic and a optical property. What does it mean? We know that every coordination compounds, it has its own magnetic and optical behavior as well as it exhibits the color. Is it right? But this Werner theory could not able to explain why the coordination compound will also exhibit the special characteristics called as magnetic as well as with the optical property as well as with the color. And also he could not able to explain how the bonds which is there in the coordination compounds will also lead into the prediction of the geometry. And he could not explain that only in the few compound he observed all these characters, but in rest of the compound he could not able to explain it. So these are the 3 drawbacks of the Werner theory. Remember children, for your examination point of view, this Werner theory has been asked repeatedly for the 3 marks. If you write all the 3 postulates, you will get a 3 marks, and again it is very, very important for the examination point of view. Hope you all understood with the Werner theory and the limitation. Next is valence bond theory. Okay. So in the valence bond theory, we are going to understand how does we can easily predict the geometry, the magnetic nature as well as with the how the entire hybridizations will be taking place in a coordination compound. It was explained in the valence bond theory. Okay, let's see what does that valence bond theory tell us. The metal atom or ion under the influence of ligand can use its N-1d and NS-NP or NS-NP and ND orbitals for the hybridization to yield a set of equivalent orbitals of definite geometries such as octahedral, tetrahedral and square planar and so on. This hybridized orbital which allow to overlap with the ligand orbital and that can donate the electron pair for the bonding, and usually it is possible to predict the geometry of a complex from the knowledge of magnetic behavior on the basis of what? Valence bond theory. So what does that valence bond theory tell us? So the valence bond theory tells us that if the central metal atom is there, if it is get influenced by the ligand by using n-1d or NS, NP or NS, NP and ND orbital, it undergo hybridization to give a hybrid orbitals. Okay. So in that, all the central metal atom which get overlap with the ligating orbitals of the ligands and give rise to the hybrid orbital. By studying that, we can easily say that what is the geometry of that complexes, and we can easily predict their magnetic behavior. So they have given a chart here to understand how does the hybridization will be taking place. If the coordination number is 4, then the type of hybridization will be sp3 and it gives rise to the tetrahedral geometry. Suppose if the coordination number is 4, then type of hybridization can also involve as dsp2 and it gives rise to the square planar geometry. Suppose if the coordination number is 5, then it involves sp3 dehybridization and gives what? Trigonal bipyramidal structure or geometry. Then if the coordination number is 6, it gives rise to the sp3d2 or d2sp3 and it gives rise to what? Octahedral geometry. So only the coordination number 6 and 4 it will be there for your board. So you are going to understand if the complex which are having the coordination number 4 or coordination number 6, how does it involves the hybridization and how does that hybrid orbitals will be looks. Everything will be understood by learning the valence bond theory. Okay, we'll see with the example so that you will understand what is that hybridization compound. So first I'll go with the octahedral complexes. Octahedral complexes are obtained by the coordination number 6. Is it right? So here I had an example of CONH3 6 times 3 plus. First I'll go with the calculations of oxidation number. We know that this is my central metal atom and it is calculated as X plus 6 into 0 is equal to plus 3 and X is equal to plus, which indicates what? Central metal atom has a plus 3 oxidation state. Okay, and we know that which is nothing but a primary valency, and that primary valency will be usually called as what? Oxidation number. First I'll go with the electronic configuration of the central metal atom. So here the central metal atom is nothing but a cobalt and it has an electronic configuration of argon 3d7 4s2. Argon 3d7 4s2. So first I'll write the 3d orbital as well as with the 4s orbital. So in a 3d we know that there are 7 electrons will be there. Is it right? So 1, 2, 3, 4, 5, 6. Why I have written 6? Because we know that it exhibits a plus 3 oxidation state. So it removes the electron, 2 electrons from the 4s and 1 electron from the 3d, and the electronic configuration will become argon 3d6 4s0. 4s0 after losing 3 electrons. Okay. Now the orbitals of the CO3 plus ions will be written like this. This is 3D, which consists of how many electrons? 6 electrons. 1, 2, 3, 4, 5 and 6. And we know that from the 4s we have removed 1 electron. Is it right? Yes. But we have understood that from the Hund's rule, we have to fill the electrons in such a way that each orbital should get a 1 electron. Is it right? That is why I have filled the electron according to the Hund's rule. But in the next step, I have written that overlapping this 1 electron from the 3D and 1 electron from the another orbital. What does it indicate? This filling of orbitals will be taking place against to the Hund's rule. That is why this electrons will be get paired up. So it gives to the 2 electrons in a 3D orbital. Now you can see that we have required how many ligands? 6 ligands we need to add up. Is it right? So for that, how many orbitals we require? 6 orbitals will be required. So I'll consider from the 3D, there are 2 orbitals. In the 4s, 1 orbital, and I'll consider the 4p. So in 4p, we know that I have considered only the 2 orbitals. Okay, you can see that there are 6 orbitals will be there, and all the 6 orbitals will be occupied by what? Ammonia ligand, and it gets paired up to give which hybridization? It is D2, because 2 d orbitals will be there and 1 s, and there are 3 p orbitals will be there. So it is D2 sp3 hybridization. You can see now in the 3D I have used only 2 orbitals, because what will happen if the cobalt which exists in a +3 oxidation state, the filling of electrons will be taking place against the Hund's rule. So once it is taking place, what will happen? The electrons which is there in the 3D which is get paired up to form 6 electrons which is get paired up by remaining 2 empty orbitals. These 2 empty orbitals and 1 4s and 3 p orbitals, you know, now it is required for my 6 ligands, and they get ligated to form a D2sp3 hybridization. Now if you see this entire structure, you can see that it involves all the atomic orbitals are get paired up. Is it right? There will be a no unpaired electron, hence it is diamagnetic in nature. Since it do not contains any electrons, they are diamagnetic in nature because all the orbitals are completely filled. Is it right? Yes. And the structure will be octahedral. And the structure will be octahedral because the centimetal atoms are coordinated by 6 ligating ligands. And also I have used the word here. You can see that inner orbital or low spin or spin paired complexes. What does it mean? During this hybridization, you can see that I have written 3D, 4s and 4p. Is it right? I am not using the next shell for pairing up with the ligands. I have used the inner shell of the 3D to form a pairing with the 6 ligating ligands. Is it right? Hence it is known as inner orbital spin paired complexes because the electron pairs are get paired up. The spin of the electrons are get paired up. Hence it is known as spin paired because it takes place against the Hund's rule. And you can see that for doing this hybridization, I have used the 3D orbitals, which means to say that which comes inner after to the 4s. Is it right? Hence it is known as inner orbital complexes. So hope you all understood with this example. We'll see with the one more example so that you will understand clearly. So we have the complexes of COF6 3- which is a hexafluorido cobalt 3 cobaltate 3. So how to calculate the oxidation number? So I'll consider X plus 6 into -1 which is equal to -3. X minus 6 is equal to -3 and X is equal to +3. Okay. So what is the oxidation state of the cobalt here? +3, and it has a 27 electron and electronic configurations will be goes like this: argon 3d7 4s2. Again, what will happen? It exhibits in a +3 oxidation state. So we have to remove 3 electrons. I'll remove the 2 electrons from the 4s and I'll remove the 1 electron from the 3d, and the electronic configuration will be written as Ar 3d6 4s0. Why, ma'am? We have to remove it because we are doing the hybridization by removing the 3 electrons from the cobalt because it is a central metal atom. You can see here in the 3D how many electrons will be there? 1, 2, 3, 4, 5 and 6, and we know that we have removed the electron from the 4s. Now if you see that the spin pair of electron which is not get paired up because it is a strong ligand. Okay. So now what will happen? You can see that the 3D orbitals which consists of 4 unpaired electrons, but we required how many atomic orbitals? We require 6 atomic orbitals. It has to get paired up with the ligands. Is it right? So, I'll consider 4s, 4p and 4d. In 4d, I'll consider only the 2 orbitals and I'll consider 3 orbitals from the 4p and I'll consider 1 orbital from the 4s and which is get ligated by what? 6 ligands and hence the hybridizations will be yes, P3D2 hybridization. So, how would I write? So, it is S, how many P? 3P and D2. Hence, it is written as sp3d2 hybridization. Now, if you see that entire structure, you can see that the 3D orbitals which consists of 4 unpaired electrons, is it right? Hence, because of the unpaired electrons are there in the complexes, it can easily attract towards the magnetic field. Hence, they are paramagnetic in nature. They are called as what? Paramagnetic, and also it exhibits the octahedral geometry because the central metal atom which is ligated with 6 fluorido-ligands and which forms a 6 coordination bonds. Hence, it is known as octahedral complex. But also I have written that it is outer orbital and high spin and spin-free complexes because to do the hybridization, I am not using this 3D because here the filling of orbitals will be taking place according to the Holmes rule. But after that, the spin pair of electron will not taking place there pairing up. Okay, will not undergo pairing up. So that I will use the next shell by considering 4D. Hence, it is known as outermost shell complexes or outer orbital complexes, which is also known as spin-free complexes because the spin electrons which is not get easily paired up because of the weak ligand. Because of the weak ligand, will not undergo the spin pairing. Hence, the spin pairs are free. Okay. Hope you all understood with the octahedral complexes. We'll see with the tetrahedral complexes also, which our coordination number will be usually 4. I'll go with tetrachlorido nickelate 2 ions. Now, the first step is we need to calculate the oxidation number of the nickel. So, I'll write X plus 4 into minus 1, which is equal to minus 2. So, which is equal to X minus 4, which is equal to minus 2 and X is equal to plus 2. So, plus 2 is the oxidation state of what? Nickel, which is a central metal atom, which is get ligated by 4 chlorido ligands. Is it right? Now, I'll write the electronic configuration. So, the nickel has 28 electrons. So, the electronic configuration will be goes like this. Argon 3d8 and 4s2. And from the oxidation number calculation, we have understood that it will loses how many electrons? Only 2 electrons. So, I can remove the 2 electrons from the 4s and I can write the electronic configuration as argon 3d8 4s0. Okay. Now, if you see the 3D electronic configurations of nickel 2 plus ion. So, 1, 2, 3, 4, 5, 6, 7, 8. 6, 7, 8. So, there are 8 electrons will be there in 3D and we have removed the 2 electrons from the 4s and 4p will be remaining. Now, you know what will happen? We required how many ligands now? From this example, we can understood that we required 4 atomic orbitals which has to be get occupied by the ligands. Is it right? Hence, we can see that I have used the 1 4s and also have used the 3p and which is get occupied by the 4 chlorido ligands. Hence, the hybridizations will be written as sp3 hybridization. It undergo what? sp3 hybridization because what? It uses 1s and 3p orbital. Hence, it is sp3 hybridization. Now if you see this entire complexes, you can see that in the 3D we consist of two unpaired electrons. If unpaired electrons are there in the complexes, we know that it easily attracted towards the magnetic field, hence they are paramagnetic in nature, and it exhibits which complexes structure? It will be exhibits in tetrahedral geometry. And you can see that here the nickel, which has been got 4 coordinated bond from the 4 chlorido ligands. This is how the nickel, as well as with the octahedral complex, we can understand that how the complex will be formed by writing this hybridization. Again, this has been asked repeatedly for the 3 marks. You must know that. So you have to practice 4 complexes, 2 from the octahedral and 2 from the tetrahedral complexes. We have one more example with the square planar complexes. Okay. So the example is tetracyanidonickellate 2 ion, and oxidation state of the nickel. Again, I'll consider this as X plus 4 into minus 1, which is equal to minus 2, and X is equal to minus 4 is equal to minus 2, and X is equal to plus 2. So the nickel has exhibit in a plus 2 oxidation state, and it consists of 28 electron, the nickel, and the electronic configurations will be goes like this: argon 3d8 4s2. You can see that it consists of what? The 2 as the oxidation number, so it can loses how many electrons? Only 2 electrons. So I'll remove the 2 electrons from the 4s, and the electronic configurations will be goes like this: argon 3d8 4s0. Okay. Now, if you see this orbitals in the nickel 2 plus ion, so the 3D will consist of 8 electrons, is it right? Yes, 1, 2, 3, 4, 5, 6, 7, 8, and 4s will be empty, and 4p I have written. But here you can see that it has been occupied by cyanido ligand, is it right? So the 4 cyanido ligands are very strong, hence their spin pairing will be taking place against the Hund's rule. The spin pairing will be taking place against the Hund's rule. So these 2 electrons will be get paired up in a 3D. Now we require how many atomic orbital? We require 4 atomic orbital which has been occupied by the ligands. 4 ligands, is it right? So I'll consider 1 D and 1 4s and 3 P. So the hybridizations will be goes like this. It is D1 and S1 and P3. So it is DsP3 hybridization. So why I have written DsP3? Because it uses 1 orbital from the D and 1 orbital from the S, and it requires 3 p orbitals in order to fill with the 4 ligands. So the hybridizations will be DsP3 hybridization. So you can see that I have written the entire reactions. So from that we can easily understand that it undergo DsP3 hybridizations, and it is clear from this is there will be a no unpaired electron, hence it is diamagnetic in nature and exhibits in square planar geometry. Okay, this is how we can easily predict the geometry, their magnetic behavior as well as their hybridizations only by understanding the valence bond theory. Okay, so by the next class again we are going to discuss with the magnetic property of the coordination compounds. So by this, I like to say that what all the things I have covered in this session, it is very, very important for the examination point of view, especially with the Werner theory as well as with the applications of ABT are too important. I have discussed with the 4 different examples. All these 4 different examples are too easy. So practice well, make a note and do well for your board. Thank you. We'll meet you with the next session. Till that, take care. Thank you.